started. I think a few more people will be joining us as we go. Welcome everyone to the informational webinar for data analytics for the process industries. My name is Alan Rossiter. I'm Executive Director for Educational Program Development with UH Energy here at the University of Houston. This particular program, though, the key architects and developers are Dr. Mark Darby and Professor Mike Nicolau. Mark is an independent consultant principal for CMID Solutions. He has worked extensively in the petrochemical, refining, and oil and gas industries for over 30 years and has a lot of experience in the application of advanced process control and optimization. And much of his experience has been with companies you may be familiar with, SetPoint and Aspen Tech. So he comes with a great strength, a great amount of experience in the whole area of data analytics. And Mike Nicolau is professor and associate chair in the Department of Chemical and Biomolecular Engineering and has a joint appointment with the Petroleum Engineering Department here at the University of Houston. He has over 30 years of R&D experience in computer-aided systems engineering with applications to energy, health, materials, and other industries. And I'm going to basically stay out of the way for most of this webinar and let them tell you more about this course. But if you can take us to the next slide, please. I just wanted to give you a few brief housekeeping instructions before we do that. So please, if you would, during the presentations, stay muted and keep your video off. That will minimize background noise and also save bandwidth. And if you have any questions that you'd like to pose, please put them in the chat box and I will monitor that and field them to the speakers as we go. So with that, I will hand over to Mark to kick things off. Next slide, please.
Okay, thank you, Alan. So when we when the subject of data analytics comes up, a lot of terms are used and thrown around, and I've listed some there: data science, artificial intelligence, big data, industry 4.0, and then associated with many techniques. So a key question is, what does data analytics mean for the process industry? Next slide, please. And as we look at it, it's really a collection of disciplines and underlying techniques. And we've listed the main contributors there to the right, including probability and statistics. So including such things as descriptive statistics, regression modeling, chemometrics is a discipline that came out of the chemical analysis area with a focus on dimension reduction and including some techniques, PLS, partial least squares, for example, and PCA, or principal component analysis. Data science, when we think of data science, we usually think of aspects of artificial intelligence, including machine learning, nonlinear regression, but also including image processing and pattern recognition. Optimization, many of the techniques we'll use will include an optimization or have an optimization aspect. For example, when we think of least squares, we're solving an underlying optimization problem. Of course, the results, a model result, can then in turn be used to optimize, to find, for example, a best operating condition or a most profitable operating point. Also important is to bring in domain knowledge. So this is where we want to use our engineering knowledge, our process understanding and knowledge to interpret the results. So critically important when we're doing anything that's empirical based is to bring that kind of analysis and focus on the problem, ensure we're interpreting the results correctly. Okay, next slide, please. So the value proposition is really one of making better decisions for more effective use of data, ultimately improving the bottom line And so how? So we want to use selected soft techniques that have been developed from the last few decades. We in effect want to leverage the less expensive, more powerful computers and the new sensors that are available today. Next slide. So the course objectives is to introduce a range of techniques that are applicable to the process industries. These would include both proven techniques as well as those that have been emerging over the recent history. We'll be providing guidance on when to use a particular technique, pitfalls to avoid with the data, those techniques, as well as the interpretation of the results. We'll discuss and show how to include process knowledge in the interpretation of those results. We believe this will help those attendees respond to company initiatives in the area of data analytics. Next slide. So, applications. Well, it's really about using data with appropriate techniques to get us to models. And so this includes things in the monitoring area, looking at real-time data and using that model to interpret current results. Fault detection, classification, diagnosis, or control. The data that is used in data analytics can come from first principle models. Those may be in the form of simulations. We may be using historical data, or leveraging the data that we already have available. We'll refer to this as undesigned data because normally that's nothing special is done as part of the operation that's operating to meet production goals. But we may also have specifically targeted data, experimental data, which actually be designed to get to learning a relationship of interest or something similar. It could be data from multiple sources, so combinations of the above, or including such things, or in addition to what we think of as, say, operating data, could be data associated with engineering design or involving operating logs and such things. All right, at this point, I'd like to turn it over to Mike to discuss some examples.
Thanks, Mark. I was muted, sorry. So as Mark mentioned, this is a field, the data analytics field is one that has been growing steadily over recent years. And we are now at the point where there is a plethora of techniques and software and data to deal with so that all of these can be used profitably in process industries. Some of the methods used in process industries have been around, and of course they have been refined over the years. They have become more powerful. Algorithms are more efficient, more effective. They can handle more situations. Software may be easier now to use, and the bottom line is that the impact of these methods has been steadily increasing. So rather than, I should also mention that this progress experienced in process industries of using more data to make decisions that are guided by the data is a general trend in many aspects of our activities today. I'm sure you all have visited the internet, and on a website you try to buy something and you get suggestions that whoever browsed that page also looked at this and that. And then the next thing you know, you go to your Facebook account and you're flooded with advertisements that say, well, we sell this kind of shoe at this size and this color and all that. So all of these are instances where data and data analytics is at work behind the scenes, and there can be a lot of sophistication in the techniques, especially in techniques that have been developed recently to a point that they can do things that were impossible years ago, such as face recognition, for example, or speech processing. But even for process industries, there have been things that are no less impressive. For example, here is a situation in a polymerization process. So here is a process that produces PET, stuff that people use to make plastic bottles, among other things. You have here the two reactors for esterification. Can you see my cursor moving, by the way? Can anybody answer?
No. Oh,
No.
wait a minute. Yes, do now. I do.
You can, right? No,
Yes.
the dark one.
Yeah.
Okay, good. Okay, very good. So there are reactors, and then there is a low polymerization reactor, a high polymerization reactor, and what you produce has a certain viscosity, and you want to maintain that viscosity, and you can measure that online, or you can find a relationship that maps all of these data points provided by corresponding sensors that I have highlighted in yellow there. This mapping produces an estimate of the viscosity based on a universal approximator, which I'm sure you'll have heard about, an artificial neural network, which is what this picture here on the right from all of these sensors to the neural network, which has in the meantime been trained to produce an estimate of the viscosity. And then that estimate is used to close the loop and take some action through a programmable logic control system, a PLC, and that's what this shows. Very simple in its operation and conceptually. There are lots of interesting details on how to do that well. This is technology that has been around, by the way, for a few decades already. It has now been improved and refined, and I'll show you a couple of examples on this in a second. So the next slide shows another application of other ideas related data analytics. This figure on the left shows spectroscopic analysis of various fuels. So this axis here is wavelength, and this is intensity. So the intensity as a function of wavelength turns out to be a signature of various fuels. So how can you, well, the human eye can just look at these images and visually tell that they can be clustered nicely and there are similarities between among these or among these or among these and so forth. How can the computer do that? Well, there is a technique that has been around for a long time, and it has now become a de facto standard. Even undergraduates now can be taught that technique in its very basic form. And Mark alluded to that, principal component analysis, which gives you points in a 2D plot. So you can visually say, well, these are fuels of one kind, these are fuels of another kind. Not only that, you can also take the kind of fuel that you have, and if I may have this next slide, please. Separate categories in various ways. Here is a separation of fuels according to a line here, if I may draw the line.
Yeah, actually, Mike, I have to say we're not seeing your cursor, and I think I understand why. So
Okay, now
I think oh, there you go. Oh, great, we got
you
it.
see the annotation, right?
Yeah,
yeah,
yes,
excellent. I have to pick the cursor for the annotation, so I picked something
well done.
else this way.
Good, good.
So now you see there is a line here that separates those two different classes of fuels that you get from the analysis of principal components. And quick parenthesis, this technique relies on something called the singular value decomposition. You take a matrix, you take another matrix, you find its eigenvalues, those are singular values. Eigenvalues are a thing that lots of companies do these days. Google, for one thing, uses this idea in their famous PageRank algorithm that made Google in the early days. So here we use it for something else. And here you can see how the neural net has these at the top here showing one category, these at the bottom showing another category. Not only that, you can also take your principal components and create a model and try to predict the circles by the axis there in the model that you build, and that, with all caveats, works reasonably well for that particular example. let's go to the next one, though, to see something that I already advertised, namely imaging analysis is something that is being done more and more. You can take, say, a flare, and by what you see in a camera, you can tell whether you have the right flare or not. Or you can take a reactor, or you can take images such as these. These images that I'm showing. Well, let me put, now you can see the mouse, right?
So no, right not.
No?
No.
The dark, okay, I'll try something else. Okay, so these images here are images from a plasma etching reactor, and they basically refer to how quickly you etch a silicon wafer. Very similar images you can get in, say, a tubular reactor, where this is a cross-section of this tubular reactor, and you see how the concentration or the temperature varies. Or you can have lots of applications like this. Well, it turns out you can get dozens of these, and you can represent all of these as a linear combination or 2 or 3 so-called principal components. Here is one principal component. Here is another principal component that you can use to represent the data. And from this, you can actually draw conclusions. Am I in the right category? Is something abnormal about to happen? Is quality of what I'm producing acceptable? And so forth. So I try to summarize here. I barely scratched the surface of something that is related to data analytics. Needless to say, there's lots and lots more to cover in this area, and how you actually do that stuff is something we will be covering in the course, using part theory, part software, part examples, and we aspire to have some industrial guest speakers actually to share, for them to share their stories with the students. With this, I'll turn it over back to the host, and if there are any questions at the end, I'll be happy to address them.
Thanks, Mike. Let's just go back to the previous slide, please, Lee. So I guess what I would just ask you now, so looking at this particular example, how would you actually use the results of your analysis once you've got it in this particular case? What sort of applications do you have?
Interesting. So let me tell you specifically where we used these. One was to certify that a tool that was sent to a customer was indeed capable of meeting specifications. So you would, what was the problem there? People would test one thing at a time. And they would say, okay, this passed, this passed, this passed, this passed. They would ship the exact 2 same reactors to the customer. The one customer would come back and say, I'm very happy, this is working great. The other customer would come back and say, well, this is not working half of the time, it's failing. Why was that? It was because what the reactor does is actually a combination. It's the result of a combination of factors. And what happens eventually can be analyzed in the same plot that I showed before. You put points here in a plot that has 2 principal components. And if everything you get is here in the green area, everything is great. If not, if it's in the excess here, things are not very good. So it was a great diagnostic tool that was eventually bundled with the equipment that the company was sending out to customers, and they could certifiably have the expected behavior. So that was the first application. And another interesting application is directly related to how you use these images. So the designers of that company were trying to redesign a reactor so they could get extreme uniformity, namely to have a color on these surfaces that would be exactly the same color for exactly uniform reaction rate, etching in this case. They tried one thing after another, after another, after another, and they couldn't get the desired uniformity. And we're talking about 0.0 something %, very, very, very tight specification. Well, I had a student who was working on this project, and at a certain point that he found that the 3rd principal component had a shape like this here, with intense color of this shape. Well, it turned out that this was exactly the shape of an antenna in the reactor, which prompted people to think that maybe this antenna is what is causing a tiny bit of uniformity. So maybe we can redesign that antenna to make it like this. Problem solved. So these are just a couple of instances where these ideas have merit. We have applied them, and not just us. I mean, many, many, many groups have applied these ideas to various applications in our group. We have done this for shale gas wells, for cementing oil wells, or for cementing gas wells to avoid fugitive methane emissions, which is a potent greenhouse gas, and all kinds of applications like this.
So basically taking data and just drawing insights from it that's not obvious to the naked eye is really what you're saying in these cases.
Exactly, yes. You get some help to identify patterns, and granted, most of these patterns, the user actually could have anticipated, and that's fine. In fact, it makes sense and it's reassuring. The real value comes from the fact that sometimes you get patterns that you hadn't anticipated, and then if you think about it, most of the time it makes sense if you have done the work correctly.
Right.
And we had such instances in terms of developing qualitative recipes for cementing gas wells, like I said, and it was, yeah, check, check, check. Yes, I knew this, I knew this, I knew this, I knew this. Whoops, that's strange. Why is it like this? Well, it turned out actually it was correct. It was a correct suggestion.
Yeah, usually mathematics turns out to be pretty good. Great, excellent.
So these are empowering techniques. These are not techniques that replace the human, but they empower the human.
Right, good. Mark, do you want to chime in on any areas where you've seen applications like that, where they helped bring new insights to old problems? You still with us, Mark?
You're muted.
There we go. Okay. Yeah. Maybe just to mention the use of such an approach in real-time monitoring. So another way of using this is defining what normal is. And that's from the data, from representative data, you get an idea of the relationship between variables, actually expressed in terms of variances or covariances between variables in the multivariable case. So when you have a situation where that relationship changes, that's indicative of a potential problem that may need to be analyzed further. Sometimes that can be very useful in combining it with other measurements that may actually predict or kind of forecast a potential problem coming in the future.
So these are what, in things like plant operations?
Yeah, so it could be, looking at a particular process unit, a compressor or a reactor, basically getting a fingerprint of what normal operation is for that reactor. And if things change, then these techniques are usually pretty sensitive of picking up changes from that sort of normal or base condition.
Right. Okay. Yeah. Good. Good catch. Any other questions from anyone in our audience? If you'd like to unmute yourself and ask a question, that's fine. But I've got a few more minutes if anyone would like to ask. Or if not, I guess we can close the session. I certainly hope you've got information that's helpful to you. Anyone have a question? I see one or two people have unmuted.
Yes, I had a question.
Yeah.
So I mentioned earlier that I'm in biopsychology, and I wanted to know if I'm very interested in taking this course because I've always been interested in data analytics, and I've taken a couple of data analytics courses, and I was wondering if I would be accepted for this course even though I'm not in this field.
So we certainly try to keep an open mind on people coming into courses, because very often there's very valuable, you might call it cross-fertilization of ideas with people coming in from different backgrounds. I guess the only caution I would give you is understand that the focus here is going to be on the process industries, and there will be some technically oriented content. But as long as you come in, with open eyes and realize that it may not be primarily in your background related directly to all of your background, you should be okay. Mike, did you have some comments on that?
Yes, in fact, we could have planted that question actually, because it's interesting that some of the techniques that are widely used in data analytics actually blossomed first in psychology. Of these, I would say principal component analysis blossomed in psychology. And that's why the term loadings and scores comes from psychology, because psychologists would actually take surveys and they would have data and they would tabulate the scores of certain subjects and then the loadings that they would load to the analysis, blah, blah, blah. So long story short, psychologists have been very, very good at using these techniques. And not just these. If you go to the work that psychologists in somewhat more interdisciplinary areas, such as, say, economics and psychology. I mean, Daniel Kahneman or Amos Tversky, or a bunch of those people who have tried to combine an analysis of human behavior with optimal decision made in economics. Well, they have come up with ideas that are mainstream in data analytics, such as reducing dimensions of large data sets, or doing statistical analysis and doing Bayesian statistics. If I know the probability that B gives A, what is the probability of A given B? Or analysis of models. Well, I have those basic factors that could affect, let's say, how long you keep your hair black, for example, over age. How do these factors relate and affect this behavior? And so forth. So there are very, very intimate and tight relationships between psychology and data analytics. And I would definitely hope that there would be a two-way communication if you elect to attend this course that we are offering.
Thank you. Thank you very much.
I noticed there's another question in the chat here, and I'll read it out. But Gabriel, you can add to this if you like. Any applications in nuclear reactor operations and engineering? So that was the question. I don't think we have any specific examples in the course, do we, Mike? Or do you see some parallels specifically to the nuclear field? I'm sure there are, but yeah.
No, I don't have anything specific on nuclear reactors. We do mention nuclear reactors because they are a prime example of a process that by itself is unstable, and you need the control system, and you need a redundancy in the control system. And then there are ways to analyze the stability of all of these systems, but we don't emphasize that in this course. It's a little bit outside the typical chemis main focus, but definitely techniques about stability and operation and safety and detection of abnormal situations. Yeah, those do apply to nuclear reactors.
Right. So it's not a main focus in the course, but certainly some concepts that are very closely aligned.
Yes, exactly right.
Okay, good. Mark, anything to add?
No, just maybe a specific thought is that, monitoring reactors, sometimes there's some fundamentals that you're interested in perhaps understanding or predicting in real time. And you have measurements around that reactor, or maybe you have a rigorous, complicated model that you're looking to extract that knowledge and come up with a simpler expression that would be amenable to real-time calculation and monitoring. So that we have some examples in that area, so that something right in that area might apply.
And actually, we have quite a few more questions popping up here. So one from, and I apologize if I get the name wrong, but Prithwaite, is it? Asking about advanced process control applications. And I kind of think that's sort of in your wheelhouse, Mark.
Okay. Some of the models we'll be looking at developing, some will be steady state models, some will be dynamic. So a dynamic model might have, certainly application towards process control. One of the examples that we have is similar to what Mike covered for the polymer reactor, and that's really the notion of a soft sensor or an inferential, where you have say a lab value that you want to control, but yet it may only be measured infrequently, maybe every 8 hours or once a day or even less frequently. But you'd like to have a continuous type measurement that you could actually control against. So one of our examples would be developing a soft sensor model for control.
Great. And there are
Yeah,
a couple. Sorry, carry on.
if I may address this also.
Yeah,
So
yeah.
yeah, process control and advanced process control in particular is fairly well covered at U of H. It's an activity represented actually in many departments in engineering, not just chemical, but also mechanical and electrical. But in chemical, it's also strong. We offer an advanced control course every other year. It's very well attended by students, not just from chemical, but also from other departments, mainly for the process orientation of the course. The process control course, of course, it's for graduate students and it has its own focus and breadth. So in this data analytics course, as Mark mentioned, we do touch upon this idea and we do intend to cover additional aspects of it in the silver and the higher belts for this program, depending on interest that we see from the students. But it's definitely an area that we are very well tuned to so that we can cover it.
Great, thanks. Another question here, and there are actually quite a few more in the chat now. And I will see how many we can get in. I know we've already passed our notional endpoint, but how often is machine learning used in process engineering, specifically building classifier models? That was the question. So.
Yeah, can I address this?
Yeah, please.
Well, it depends. There are some classifications which have been classic, no pun intended here. So whether a fault is about to occur or not, it's a classic task that engineers, chemical engineers, of course, as well, have been toying with forever. So this is one typical classification. And then you may have the next steps, which are after you detect that a fault may have happened or is about to happen, you may want to diagnose what is the culprit. So you want to say this is likely, that's how I classify this kind of fault and all that. So these are methods that, this is an area rather for which methods have been around for a long time. There is an old paper, mid-90s, by Han and Stephanopoulos, where they cite 11 different classes of models that one can use to do classification of faults. So it's a rich area. There is no single solution to the problem, and it's one where engineers definitely have to contribute because they contribute domain expertise and understanding. So how frequently is classification used? Well, maybe not as frequently as in other applications where you have image processing, for example, where you want to say, I look at a cat or I look at a dog. Here you may want to say, I look at a flare that will pass EPA standards or that will not pass EPA standards. But this is a slightly different task because you can have actually single quantitative measures that you can use for these types of classification problems. So it is used to a reasonable extent in process industries, maybe not as much as in high tech with image, speech, and other kinds of recognition that is now very widespread.
I have a follow-up question to that.
Mm-hmm. Yes, please.
So if a classifier model is used, like what would be the best? Maybe like logistic regression or random forest or?
That's what I was trying to allude to. There is no universally best. To give you an idea, we had pretty good luck. I'm just going to mention one project. We had pretty good luck with PLSDA, and don't worry about what the acronym means. It's a particular technique that uses partial least squares and discriminant analysis to use data, build a model, and tell you this well is going to leak methane or this well is not going to leak methane, and do this kind of classification. Is this the best method? Well, certainly not universally. There are all kinds of different methods, from neural nets, from deep learning neural nets, to simple linear classifiers with a long linearity at the end, and other things that one could use for classification. So there is no
Okay.
universally best solution here.
Great, thanks. Thanks, Dr. Nicolau.
And I guess one somewhat related question, I think, also any applications of data analytics and images that could help increase efficiency and lower the cost of shale fracking. So very specific there in that application. Sounds like you've done some oil field type work in the past, Mike.
Yeah, well, this is an area where I've spent a lot of time actually in the last, 20 years or so. Imaging analysis, I don't know. We haven't used much of this for analysis of 2D images for fractures. I know that others have done this, for example, to analyze core samples. You get a core, you look at an image. Is this from shale? Is this from carbonaceous rock or other kind of rock? What is it? There are all kinds of applications like that. For what we have done, we have analyzed 1D profiles. Like, since you're knowledgeable, I presume you probably know ARP's equation for the decline of an oil or gas well. Well, it turns out you can derive an equation based on data alone. What is the magic curve that actually describes the decline of production in a well? And it can give you this essentially science discovery, so to speak. I'm using a heavy term there to indicate something simple, that you have lots of data. Well, you see lots of instances of a pattern, so you can find what that pattern is. That's what this does, basically.
Great. One more question here, and I think we will stop at, I see another one has just popped in. Okay, so one more question here was just asking about monitoring greenhouse gas emissions and climate change events. So, have you got experience with using data analytics in that field as well?
Well, I know that developing a data-driven model for plant emissions, I was thinking more of in terms of pollutants is something that's been done routinely for a while. But with the importance of GHGs now, I know these methods are being extended, that will be extended to cover that as well. I'm trying to think of specific applications. I think I've just heard in general that they're being applied to GHGs in a plant and potentially a company-wide perspective.
Great. Okay, thanks. Okay, I think probably it is time. Well, let's say we've overshot our official time, but as for those of you who are still here, thanks for sticking with us. I think we had some very interesting questions there, and I didn't want to cut those short. But I would just like to wrap up then just by making sure you're aware of the details. And perhaps, Kyle, if you can put those links in the chat as well, that would be helpful for us. But data analytics for the process industries starts on August 31st and runs through November 11th of this year, of course. It will be on Tuesday and Thursday evenings, and it will be online, 6 to 8:30 p.m. So that's where the program is going to be for you. Let's say the links are now in the chat. So you can get more information if you need it from the website, or go directly to the application form if you'd like to register for the course. Next slide, please. And so, yeah, thanks very much for your time. And we do look forward to seeing you and maybe some of your colleagues when we start data analytics for the process industries on August 31st. So with that, thanks very much, everyone, for joining us.